Hello, our names are Jacob Peterson, Joshua Hayes, Abraham Paredes, and Christopher Fong. We are from the University of Michigan-Flint, and we are seeing how the number of fins affect a heat exchanger on their performance. The modification to the TD1007 heat exchanger experiment that was selected was intended to explore the effect of the number of fins on the performance of the heat exchanger. This question was developed when performing Part 5 of the TD1007 experiment, the difference between finned and unfinned heat exchangers. During this experiment, the question was raised, to what degree does adding fins increase efficiency when fins were already present? This is similar to the question answered in Part 5 of the TD1007 heat exchanger experiment, but instead of comparing finned and unfinned, it compares the already finned to a more finned version. This experiment will be run twice using the same parameters. The only difference will be the heat exchanger in the system. The heat exchangers used will have 16 tubes. One will have 6 fins evenly spaced. This is the version from the factory. And the second one will have 12 tubes evenly spaced. One fin added between each original fin. As you can see, there's a little picture. We used a little thermal paste to increase the conductivity of the fins on the tubes, as we could not take the heat exchanger apart and add these fins, so it was difficult to put them on the heat exchanger itself. The heater take temperature will be set to 60 degrees Celsius. Water will enter the heat exchanger from the bottom and exit through the top. VDAS data acquisition will be used to record several quantities, including the temperature of the water at the inlet, the heat exchanger, as well as the outlet, the temperature of the air in the room, and the temperatures just before entering the heat exchanger and just after. The VDAS will also calculate other required values. This is a little picture of the VDAS software that we use to collect data. As you can see, we also have the heat transfer coefficient, as well as mean temperature efficiency and airflow rate, mass airflow rate that is, as well as other values that we used during this experiment. The water flow will be set to 0.25 liters per minute, and the airflow will be the controlled variable set to 250 pascals all the way down to 25 pascals. We did this for both heat exchangers. Here is a little demonstration of our experiment in action. As you can see, as we were running it, we had the temperature set to 60. It was floating around at 59.7 during this specific instance. These little green boxes had our temperatures for our water and as well as our water flow rate, and it also had the temperatures of our airflow and our mass airflow rate. This is the result of the 6 fins. We have the power absorbed over emitted in watts as compared to air mass flow rate. We also have the heat transfer coefficient and air and water and mean efficiency versus the air mass airflow rate. Our results on the 12 fins showed that the power absorbed by this heat exchanger in watts over the air mass flow rate, as well as the heat transfer coefficient, are just ever so slightly higher. As evidence from these graphs, as said before, the addition of fins increased the heat transfer coefficient and the power absorbed by the air, and the power emitted by the heat exchanger. It did not increase the efficiencies of the heat exchanger, contrary to expectations. One possible reason for this is the presence of the thermal conductivity paste. It was used to increase the surface contact between added fins and the tubes. It formed irregular shapes, however, which may have disrupted the airflow through the heat exchanger. Another possible source of error is the aforementioned surface contact. Although the thermal conductivity paste was used to improve that, the contact was not as seamless as that of the manufacturer-provided fins. That is the result of our experiment. was a lot of fun, especially constructing and running the experiment, and I hope you learned something.